A shoelace looks almost primitive, a thin cord woven from cotton, polyester, or nylon, threaded through a series of small holes, tied into a simple bow. In an age of magnetic clasps, molded plastics, and micro-adjustment dials, it feels outdated, and yet it persists. To understand why, we have to step back to what footwear required before laces became standard. Early shoes were often secured with straps, toggles, or buckles. Leather straps wrapped around the foot and ankle, buckles cinched tight. These systems worked, but they shared a limitation: fixed tension. A buckle closes at specific holes. A strap fastens at defined increments. Once secured, the pressure remains largely static. But the human foot is not static. Feet expand throughout the day. Blood flow increases with movement. Muscles flex and contract. The shape of the foot changes subtly during walking or running. Even temperature alters volume. A rigid fastening system cannot easily adapt to those shifts. Shoelaces introduce distributed adjustability. Instead of securing at a single point, they distribute tension across multiple eyelets. The crisscross pattern creates a ladder of tension zones. Each intersection transfers force diagonally across the shoe's upper material. The moment of realization comes when you see the lacing pattern not as decoration, but as a force network. Each crossing is a pulley of sorts. When you pull the lace ends, tension redistributes along the entire row. You can tighten near the ankle while leaving forefoot space looser. You can skip eyelets to reduce pressure on certain areas. A single continuous cord offers infinite micro-adjustments. This flexibility is something buckles and buttons cannot replicate without complexity. Then there is the question of material. Why woven fibers instead of solid strips? Because friction matters. Shoelaces rely on friction both against the shoe's eyelets and against themselves in the knot. The woven structure increases surface area. It creates tiny irregularities that resist slipping. Flat laces, commonly used in athletic shoes, increase contact area even further. Their width spreads pressure across the tongue of the shoe, reducing localized discomfort. Round laces, often used in dress shoes or boots, slide more easily through eyelets, allowing smoother tightening. This is not random. Flat laces prioritize stability. Round laces prioritize smooth cinching. The choice reflects the intended use of the shoe. Athletic shoes demand stability during dynamic movement. Dress shoes prioritize appearance and occasional wear. Then there is the knot. The bow knot is ubiquitous. It is quick to tie and quick to untie. It can be adjusted without fully unthreading the lace. But why not use a more permanent knot? Because failure is part of the design. Shoelaces are meant to loosen before injury occurs. If laces never slipped, a foot caught on an obstacle could experience greater strain. A knot that can be untied easily also reduces the risk of circulation restriction. The bow knot holds under steady tension but can release under sudden force. This balance between security and reversibility is deliberate. Human behavior also shaped lace length. Too short and tying becomes difficult. Too long and loops drag on the ground. Standard lace lengths correspond to the number of eyelets in a shoe, reflecting ergonomic reach and typical tying motion. Eyelets themselves influence lace performance. Metal grommets reduce abrasion. Reinforced stitching prevents tearing under repeated tension. The placement of eyelets aligns with the anatomy of the foot, closer together near the ankle for greater control, spaced slightly wider across the midfoot. Shoelaces also accommodate swelling and variability. Imagine a rigid closure system molded to a specific foot shape. It might fit perfectly at first, but discomfort would grow with movement. Laces allow subtle shifts in tightness throughout the day. They are not merely fastening devices. They are dynamic adjustment systems. Consider alternatives that have emerged. Velcro straps offer convenience, but lack micro-adjustability across multiple zones. They secure at 1 or 2 points. Over time, the hook and loop material degrades. Dirt reduces adhesion. Zippers provide quick closure but lack tension control. They fix the shoe to a predetermined shape. Elastic slip-on designs eliminate tying but sacrifice adjustability entirely. Modern dial-based systems, like those seen in some cycling or running shoes, attempt to replicate lace tension with cables and ratchets. These systems allow precise adjustments but increase cost and mechanical complexity. They can fail catastrophically if internal components break. Shoelaces, by contrast, fail gracefully. If a lace breaks, it can be replaced cheaply and easily. If it loosens, it can be retied in seconds. It does not rely on hidden mechanisms. The apparent simplicity conceals resilience. There is also a manufacturing advantage. Laces are inexpensive to produce. They require minimal material. They can be standardized across brands. This reduces production complexity while maintaining flexibility in design. Shoes can be made in countless shapes and sizes, but the lacing system remains consistent. This modularity matters. If a shoe relied on a proprietary fastening mechanism, repair and replacement would be more difficult. Laces create a universal interface between user and shoe. The crisscross pattern also stabilizes the shoe upper. When tension is applied diagonally, it pulls the sides of the shoe inward evenly. This distributes stress across seams and panels. A straight vertical lace pattern would concentrate force differently and reduce stability. Even the choice of aglets, the small plastic or metal tips at the ends of laces, reflects design necessity. Without aglets, the lace ends would fray, making threading difficult. The aglet stiffens the tip, allowing easy insertion through eyelets. It is a small detail, but it prevents daily frustration. Shoelaces also adapt to fashion. They can be swapped for color, pattern, or material without altering shoe structure. This adaptability contributes to their longevity as a fastening method. They serve both functional and expressive purposes, but beneath fashion lies physics. The friction coefficient between lace fibers determines knot security. The elasticity of the material affects tension retention. Too elastic, and the shoe feels unstable. Too rigid, and tying becomes difficult. Manufacturers tune these properties carefully. The aha moment often occurs when you realize that shoelaces are not simply holding shoes on your feet. They are managing distributed tension across a flexible structure that changes shape continuously. The shoe upper bends and flexes with each step. The lace must allow that movement while maintaining snugness. It must stretch slightly, but not permanently deform. That balance is subtle. The reason shoelaces have not fundamentally changed for centuries is not lack of innovation. It is because the problem they solve has not changed. Human feet still swell, movement still redistributes pressure, shoes still require adjustable tension. Laces remain the most efficient way to accomplish that with minimal hardware. Invisible design thrives in mature solutions. When something appears outdated yet persists, it often means it occupies an optimal point in a complex trade-off space. Shoelaces sit at the intersection of flexibility, cost, repairability, and control. They are not high-tech. They are well-resolved. In an era of automation and convenience, tying laces may seem inefficient, but that small ritual gives the wearer control. It allows micro-calibration of fit before motion begins. And once tied, the laces largely disappear from awareness until they come undone. That is the mark of invisible design. When it works, you forget it exists. When it fails, you notice instantly. The shoelace does not announce its engineering. It simply holds tension across leather and fabric, adapting quietly to the shifting architecture of the human foot, a woven cord solving a problem that is both mechanical and biological. And perhaps its greatest strength is not that it has endured unchanged, but that it still works.